Imagine a machine, right? Like something the size of a small car just flying directly overhead in the dead of night.
Yeah, a massive, heavy piece of machinery.
Exactly. It's carrying a substantial payload, it's churning through the air, and well, you look up and you can't see it.
Nothing but black sky.
Right. And you listen, really straining your ears against the ambient quiet, and you can't hear a single hum. No buzz, no whine. And down on the ground, there's this multi-million-dollar military-grade thermal camera scanning that exact patch of sky.
And the screen is totally blank.
Completely blank.
Yeah.
And meanwhile, an electronic warfare sensor array, the kind designed to pick up the faintest radio waves from miles away, it registers 0 electromagnetic emissions. No radar bounce, no RF spikes, just nothing.
It completely defies our basic intuition of physical mechanics, honestly.
It really does. I mean, a heavy object displacing air, burning energy, pushing high voltage, it just inherently has to leave a footprint, right? But here, the footprint is completely gone.
And that's what makes this so fascinating. It's a total paradigm shift in how we approach fluid dynamics, thermodynamics, electromagnetics. The engineering challenge isn't just making an aircraft fly efficiently anymore.
Right. Flight is the easy part now.
Yeah, exactly. The real challenge is forcing this loud, hot, electrically volatile system to perfectly mimic the absolute emptiness of the sky around it, and doing that across every conceivable spectrum of detection.
Which brings us perfectly to our mission for this deep dive. We are unpacking a massive stack of highly technical source material today. We've got dense engineering specifications, cutting-edge aerodynamic research papers, strategic white papers, and what they all focus on is this ultimate triad of modern drone stealth.
The big three.
Yeah.
Acoustic, thermal, and electromagnetic or EMI signature suppression.
Right. We're going to look at how engineers are fundamentally cheating physics at the molecular and aerodynamic levels to make these massive platforms simply disappear. But before we get into the weeds, why should you, the listener, care about this?
Well, I mean, the reason you should care goes way beyond just the military applications. Whether you're into aerospace engineering, material science, or you just love a really intense engineering puzzle, the solutions here are just incredible.
Absolutely. Right.
Totally. We're looking at situations where engineers run into these seemingly insurmountable physical walls, like the inescapable waste heat of a high-power motor, and they just bypass them with these incredibly elegant, counterintuitive solutions. It's all about how we manipulate the natural environment to, hide within its blind spots.
Yeah. Now, real quick, before we really get into the mechanics, I do want to briefly contextualize our source material for you. The documents we're analyzing, they draw heavily from real-world combat data.
Right. Very contemporary data.
Yeah, they explicitly reference the ongoing Russia-Ukraine conflict, specific hardware platforms like the Shahed 136, and various rigid military standards for electronic shielding. So I want to be crystal clear with you. Our goal today is strictly to explore the underlying engineering.
Because the physics.
Exactly. The physics and the material science exactly as they are presented in these texts. We are absolutely not endorsing any political sides, military actions, or viewpoints associated with the conflicts mentioned in the sources. Our focus is purely on the science of signature suppression.
Yeah, I mean, the battlefield just serves as the ultimate stress test for these technologies.
Yeah.
We're simply looking at the mathematical models and the physical material responses that come out of those extreme environments.
Perfect. So let's start with the most fundamental detection method. Because before an aircraft even has to worry about, like, a highly advanced, cryogenically cooled thermal radar, it has to defeat the most basic human sense.
Eerie.
Right. It has to beat passive acoustic arrays. These ground-based acoustic sensors don't emit any radar waves that you can track. They just sit there and listen. And if you have a massive propeller chopping through the air, keeping a heavy machine aloft, you're inherently generating pressure waves. You're making sound.
You're violently displacing air, which creates coherent acoustic structures. And the systems hunting for those structures are, well, they're remarkably sophisticated. They rely on something called TDOA.
Time difference of arrival.
Exactly. They use a distributed matrix of highly sensitive microphones spread over a huge geographic area.
So if I'm conceptualizing this TDOA tracking correctly, it's essentially triangulation through cross-correlation, right? Like a sound wave propagates outward from the drone, it hits microphone A, but because microphone B is a few hundred yards further away, the sound hits it a fraction of a second later.
Right, and then microphone C gets it a fraction of a second after that.
Okay, so the system logs the precise microsecond those acoustic waves arrive at each node, and by crunching those tiny time differentials through an algorithm, it pinpoints the exact altitude, speed, and heading of the drone.
That's exactly it. The mathematics are incredibly precise. But, and this is the crucial weakness for that cross-correlation algorithm to successfully calculate the time delay, it needs a very distinct, continuous signal to lock onto.
It can't just be random noise.
Right. It cannot track chaotic background noise like wind or distant traffic.
Yeah.
It needs an acoustic fingerprint. And the most glaring fingerprint a propeller-driven drone produces is the blade passing frequency, the BPF.
The BPF, that's that specific piercing tonal whine you hear when a drone flies over, right?
Yes, that exact annoying hum.
And looking at the aerodynamics in the sources, that sound isn't just the electric motor itself. The actual physics of the noise generation comes from the very tip of the propeller blade.
The tip vortex.
Right, because as the blade shears through the air, you have this high pressure on the bottom face of the blade pushing up against the low pressure on the top face. And at the very tip, that high pressure air just violently curls up and over the edge to fill the low pressure void.
Which creates a very tightly wound mini tornado. The tip vortex is the primary culprit giving the drone away. It's a highly concentrated, coherent structure of rotating air that detaches from the blade tip and trails behind it.
And it does this rhythmically, right?
Exactly. The formation and shedding of these vortices happen at a very predictable rate based on the RPM of the motor, and that generates a powerful, narrow band noise peak. Usually in the acoustic spectrum, this peak sits somewhere between 100 hertz and 10 kilohertz.
Which is awful for stealth because that happens to be the exact frequency band where both the human ear and these TDOA microphone arrays are optimized to be hypersensitive.
It's the worst possible frequency to be allowed in.
So the whole engineering challenge here is figuring out how to generate thrust without generating that coherent tip vortex. And the sources detail a really fascinating physical modification to the blades to solve this. They call it DSDD. Double slit, double depth.
Yeah, and looking at the schematics, it is a surprisingly minute physical alteration to the geometry of the blade.
It really is. Like, they don't redesign the whole wing. They just cut a specific groove into the trailing edge.
The geometry is tiny, but its placement shows a really profound understanding of low Reynolds number aerodynamics. The specifications dictate a double width groove measuring exactly 0.12 inches across and a double depth of 0.16 inches.
Barely a fraction of an inch.
Right. But the critical variable is the radial location. This groove is placed exactly at the 0.95 RR position.
Okay, let's break that notation down for a second. The RR refers to the radial position along the blade, right?
Yes, from the center hub to the tip.
So 0.95 means this double slit is placed exactly 95% of the way out from the center, right at the outer edge before the absolute tip. I imagine if you place the slit closer to the root, like at the 50% mark, it wouldn't do anything for stealth.
Placing it anywhere else renders it completely useless. At exactly 0.95, the slit sits precisely at the inflection point, where that high-pressure tip vortex is in its most nascent, violent stage of formation.
Oh, right, as it's trying to organize itself.
Exactly. As the vortex begins to roll up and coalesce into a tight, noisy structure, it hits this double-slit geometry. And this physical groove acts as a severe fluid disruptor. It introduces a sharp pressure gradient that brutally shears the core of the vortex.
So it prevents it from fully forming and detaching as a single coherent acoustic wave. It's essentially forcing the vortex to violently collapse in on itself before it can become that stable mini tornado.
You've got it. Instead of one large organized pressure wave propagating down to the ground, you get this disorganized, fragmented mess of much smaller microvortices.
And what does the data say about how well that actually works?
The empirical data is striking. Wind tunnel testing shows that this tiny 0.12 by 0.16-inch cut at the 0.95 mark reduces the sound pressure level by a massive 7.2 dBA.
Okay, wow. To put that 7.2 dBA drop into perspective for a second, the decibel scale is logarithmic, not linear. So every 10 decibel drop represents a tenfold decrease in acoustic intensity.
Which translates to roughly a halving of the perceived loudness to the human ear.
Right. So a 7.2 dBA reduction means we are essentially cutting the perceived noise of that drone blade in half, just by cutting a tiny notch near the tip.
It's incredibly efficient.
But, you know, the obvious pushback from any aerospace engineer is going to be about the efficiency cost. Anytime you alter a smooth lifting surface by literally cutting chunks out of it, you induce parasitic drag. You lose lift.
And that trade-off is always the limiting factor. But the DSDD modification is remarkable because it only incurs a 3.96% penalty to to the aerodynamic power.
Wait, only 4%?
Less than 4%.
Yeah.
The drone loses roughly 4% of its thrust efficiency, but gains a 50% reduction in perceived noise. The sources actually refer to this as a Pareto optimal solution.
Meaning you can't improve one variable without severely hurting the other. It's the absolute optimal frontier between acoustic suppression and aerodynamic performance.
Exactly. And the research explicitly compares this DSDD method to older stealth methods, like running deep serrations all the way down the entire trailing edge of the blade.
Like a saw blade.
Right. And those full-blade serrations drop the noise significantly, sure, but they induce massive flow separation. That results in a 15% penalty to battery life and thrust. The DSDD, on the other hand, is a precision strike on the exact fluid dynamics source of the noise.
That's brilliant. And that concept of serrations actually leads perfectly into the biomimetic approach detailed in the aerodynamic research papers. Because the engineers didn't just stop at the DSDD notch.
No, they look to biology.
Specifically owls. I love this part. I mean, it's like comparing the loud slapping flight of a pigeon to the silent glide of an owl. An owl is an ambush predator that relies on completely silent flight. Unlike a pigeon, which has rigid, blunt feathers that slap the air and create these large, low-frequency pressure waves, the owl has microfringes.
Yeah, essentially a finely serrated trailing edge on its primary flight feathers.
And the engineers actually mimicked that.
They did. Biomimetics allows engineers to bypass decades of trial and error by just adopting structures that nature optimized over millions of years. By integrating biomimetic serrated trailing edges alongside that DSDD cut, they pushed the acoustic suppression into a totally different physical domain.
How so?
Well, a smooth trailing edge causes the boundary layer of air to separate uniformly, right? That creates a predictable, low-frequency shedding cycle. But these biomimetic serrations force that large, uniform separation line to break into thousands of microscopic, out-of-phase shedding events.
Oh, I see. Which connects directly back to what we discussed about defeating those TDOA tracking algorithms.
Yeah.
If you shatter those large vortices into microscopic turbulence, you are taking all of the acoustic energy concentrated in that distinct tonal whine, and you're scattering it across a vast spectrum.
You are converting narrowband mechanical noise into broad-spectrum, high-frequency white noise.
And why is that conversion so vital for stealth?
Because of how the Earth's atmosphere naturally attenuates sound. Low-frequency sound waves, because they have very long wavelengths, can diffract around obstacles. They can travel for miles through the air with very little energy loss. Think of like a foghorn or the bass from a car stereo.
You feel it from blocks away.
Exactly. But high-frequency sound waves have very short wavelengths. As they travel through the atmosphere, they rapidly lose energy due to molecular relaxation.
Molecular relaxation?
Yeah, it's essentially the friction of oxygen and nitrogen molecules absorbing the wave's kinetic energy. High humidity, temperature gradients, foliage, they all eat high frequencies incredibly fast.
So by shifting the drone's acoustic energy into high-frequency white noise, the engineers are literally using the atmosphere itself as a massive passive sound sponge.
Yes. And more importantly, that TDOA tracking array we talked about, it completely loses its target.
Right, because the algorithm is searching the cross-correlation matrix for a distinct repeating frequency fingerprint. If the drone simply sounds like high-pitched static or the rustling of leaves in the wind, there is no coherent signal to lock onto.
The signal-to-noise ratio drops way below the threshold of detection. The mathematical foundation of the tracking system just collapses.
That is wild.
It is. But to ensure this effect actually remains stable, the drone's flight control systems have to adhere to a very strict kinematic limit. The research dictates that the blade tip speeds must absolutely remain below 0.7 Mach.
Okay, the 0.7 Mach limit. This is fascinating because it really highlights the difference between the velocity of the airframe itself and the velocity of the propulsion system.
Right, they are very different things.
The drone itself might be loitering at a sluggish, 80 miles per hour, but the propeller tips, which are spinning at thousands of RPMs, are traveling exponentially faster. And if those tips approach the speed of sound, if they cross the critical Mach number, the localized airflow over the blade can't move out of the way fast enough. The air begins to compress rapidly.
And as the local flow reaches Mach 1 over the curved camber of the blade, a shock wave forms. Even if the tip is only moving at Mach 0.75 or 0.8 relative to the air, the acceleration of the air over the curved surface pushes it past the sound barrier locally.
And these localized shock waves create an immense amount of wave drag, which kills aerodynamic efficiency. But for our focus today on stealth, the critical issue is that shock waves generate high-intensity, impulsive noise.
Yeah, it manifests as a deafening, pulsating crackle. and no amount of biomimetic owl feathers or trailing edge serrations can mitigate a shockwave.
So Mach point 0.7 is the absolute red line. But wait, this creates an operational paradox, doesn't it? If you have a massive platform carrying a heavy payload, you need substantial thrust. And the simplest way to generate more thrust is to just spin the propellers faster.
Exactly.
But if you are artificially throttling your RPM to keep the tip speed strictly below Mach 0.7, how do you maintain lift without stalling the aircraft? You're artificially capping your power.
You are. So the solution lies in altering the solidity of the propeller disc.
Solidity.
Yeah, solidity is the ratio of the total area of the propeller blades to the swept area of the circular disc they create when spinning. If you are kinematically restricted from increasing the rotational velocity, your only other option is to increase the physical surface area that's moving the air.
I see where this is going.
So the engineers transition away from standard two-blade configurations. They move to multi-blade setups, 3, 4, or even 5 blades per rotor.
So by increasing the blade count, you can displace the same total volume of air, generating the required thrust for a heavy payload, but you can do it at a significantly lower RPM.
Precisely. A lower RPM ensures your tip speeds remain safely below that 0.7 Mach threshold, completely avoiding transonic shockwave formation.
Okay, but let me push back on the structural design for a second. If we are adding multiple blades per rotor and we're utilizing large propeller arcs to move air slowly, the physical weight of the propulsion system becomes a serious issue.
Mass is always the enemy.
Right. So to counteract that, these large drone blades are constructed from hollow carbon fiber reinforced polymers, or CFRP.
Yes, carbon fiber is the obvious material choice here. It offers an exceptionally high strength-weight ratio and immense stiffness. You need that stiffness to prevent the long blades from flexing and losing aerodynamic efficiency under heavy loads.
But structurally, a hollow, stiff carbon fiber shell that is the exact same acoustic architecture as an acoustic guitar body.
It is a resonant chamber.
Exactly. If you have a large hollow shell under massive aerodynamic load, absorbing the mechanical vibrations of the electric motor, it's going to suffer from severe internal resonance. Wouldn't the carbon fiber act as a guitar amp and actually amplify the vibration noise? The hollow blade would literally ring like a bell.
It would. This phenomenon is known as structural acoustic coupling, and it is a major, major design flaw if left unaddressed. The mechanical vibrations from the stator and rotor, combined with the aerodynamic buffeting on the surface, excite the natural resonant frequencies of the hollow carbon fiber shell. The interior volume amplifies the sound, and it radiates outward as this distinct, deep structural hum.
So how do they solve that? How do they decouple the acoustics from the structure without just filling the blade with solid material and completely ruining the weight profile?
The specifications call for sandwich core construction.
Sandwich core.
Yeah, the interior of the hollow carbon fiber shell is injected with highly specialized, ultra-low density acoustic dampening materials. The sources heavily emphasize the use of PMI foam, polymethacrylamide, or aramid honeycomb structures.
Polymethacrylamide foam. Okay, so they are essentially filling the acoustic cavity with a high-tech sponge.
A very specific kind of sponge, yeah. The molecular structure of PMI foam is what makes it so effective. It is a closed-cell polymer foam with an extremely high cross-linking density.
Meaning the molecules are very tightly bound together.
Right, and while it adds negligible mass to the blade, its cellular architecture is highly viscous on a microscopic level.
Viscous, like syrup.
Exactly, it resists flow or shear. When the structural vibrations attempt to propagate through the hollow space, they encounter the cell walls of the PMI foam. The kinetic energy of the sound wave physically forces the polymer chains to flex and deform.
Oh, wow.
And because the material is highly viscoelastic, this physical deformation creates internal friction. That friction converts the acoustic kinetic energy into microscopic amounts of thermal energy.
That is genius. It literally absorbs the mechanical vibration and bleeds it off as imperceptible heat.
Yes. Furthermore, by bonding this rigid foam to the interior walls of the carbon fiber, you fundamentally alter the mass stiffness distribution of the blade.
Which changes its resonant frequency.
Exactly. You shift its natural resonant frequencies far outside the operational RPM bandwidth of the motor. So you guarantee that the motor vibrations can never trigger a harmonic feedback loop.
It's an incredibly elegant passive damping system, but the documents go beyond passive materials, right? There is an entire section dedicated to active noise control, specifically a system called synchrophasing.
Yeah, synchrophasing is where the engineering crosses from material science into really advanced algorithmic control systems.
So how does synchrophasing work?
It applies the principles of active destructive interference to the macro aerodynamics of the platform. We're all familiar with destructive interference in, like, noise-canceling headphones, right?
Right, where a microphone detects incoming sound and a speaker generates an inverted pressure wave peak meets trough, effectively canceling the sound wave at your ear.
Exactly. But you obviously can't rely on headphones for stealth. Instead, the drone uses its own propulsion systems as the noise-canceling speakers.
Okay, wait, how?
Well, in a multi-rotor configuration, you have multiple propellers generating powerful acoustic waves. If those motors run asynchronously, meaning independently of one another, their sound waves will randomly overlap.
Right, it's just chaotic noise.
Sometimes they might briefly cancel each other out, but frequently they will constructively interfere. They amplify the sound, creating a low-frequency, pulsating beat frequency that travels for miles. It sounds like a rhythmic thrumming.
Whoop, 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 whoop.
Exactly. So to eliminate that beat frequency, the electronic speed controllers utilize highly precise sensors, specifically 12-bit incremental encoders mounted directly on the motor shafts.
Okay, 12-bit encoders, what does that mean in practical terms?
A 12-bit encoder provides 4,096 distinct rotational positions per single revolution.
Wow.
Yeah. This means the flight control computer tracks the exact physical angle of every single blade on the aircraft in real time, computing the data thousands of times per second.
So the system knows the microsecond positioning of, say, the left rotor's blade relative to the right rotor's blade.
And to a fraction of a degree. And using that data, the flight controller dynamically adjusts the pulse width modulation signals sent to the motors. It locks the propellers into a rigid mathematical phase angle relative to one another.
What's the specific angle they use?
It depends on the blade configuration. The sources detail that for dual-blade propellers, the control loop locks them at exactly a 90-degree phase offset. If the platform utilizes a 5-blade propeller configuration, the algorithm locks them at exactly a 36-degree offset.
And why the specific numbers?
Because by strictly maintaining those specific phase margins, the system guarantees continuous, active, destructive interference.
Oh, I get it. The acoustic pressure waves generated by the left rotor is forced to perfectly overlap with the anti-phase trough of the pressure wave generated by the right rotor. The physical sound of one engine is utilized to cancel the physical sound of the other engine in midair, before the wave can even propagate downward toward that TDOA microphone array on the ground.
That's exactly how it works. And the source data states that simply locking the phase angle with these 12-bit encoders achieves a reduction in noise of up to 19 decibels.
Wait, 19 decibels? From just syncing the spin rates?
Yes. A 19 decibel drop in an active flight environment is an astonishing achievement in control theory. It drastically smooths out the fluctuation strength and the acoustic roughness of the platform. The drone no longer produces a beating, rhythmic signature. It just blends seamlessly into the ambient background noise.
Okay, so we've essentially trapped the drone in an acoustic vault. By breaking up the tip vortices with DSDD, utilizing biomimetic white noise scattering, damping internal resonance with PMI foam, and actively synchrophasing the rotors, the platform becomes an acoustic ghost.
Completely silent.
But solving the acoustic problem inadvertently highlights a massive thermodynamic problem, doesn't it?
It definitely does.
Because we have a heavy machine generating immense power, flying against a freezing cold night sky, a high-voltage battery array, and an internal combustion system, they generate an incredible amount of waste heat. And a Stinger missile or an Igla thermal seeker, they don't care if the drone is completely silent. If the airframe is radiating thermal energy at 500 degrees Celsius, it is a giant beacon.
Yeah, thermal stealth presents a much more rigid barrier than acoustic stealth because the laws of thermodynamics are absolute. Energy cannot be destroyed. The waste heat generated by the propulsion and internal avionics must be transferred out of the system, or the platform will experience catastrophic failure. It'll just melt itself.
So the traditional engineering approach to thermal suppression, looking at the older sources, was essentially an attempt to bottle the heat up, right? They reference coating the drone's exhaust and engine compartments in low emissivity metals, like highly polished aluminum or silver-based paints.
Like the low-E coatings.
And I can understand the basic logic there. If a missile is looking for radiated thermal energy, you wrap the heat source in a material that has an incredibly low emissivity factor, meaning it refuses to radiate heat outward. It acts like an infrared mirror.
The logic holds true for short-duration suppression, sure. But in the context of sustained flight, it creates a fatal design flaw known as a heat accumulation trap.
How so?
Well, emissivity and absorptivity are linked by Kirchhoff's law of thermal radiation. A surface that is a poor radiator is also a highly effective reflector. By lining the engine compartment with low emissivity aluminum, you were essentially pointing a thermal mirror inward.
Oh, no.
Yeah. The 500-degree waste heat generated by the propulsion system hits the skin and reflects directly back into the internal
So the
cavity.
heat cannot escape. It's like a mirrored thermos.
Exactly. The internal ambient temperature rapidly spikes, and the delicate electronics, the battery management systems, and the structural integrity of the engine mounts literally cook in their own trapped waste heat. It becomes a thermodynamic pressure cooker. And eventually, that thermal energy has to conduct through the physical structure of the airframe.
It has to go somewhere.
Right. And when the thermal mass finally breaches the structural threshold and conducts to the exterior skin, it causes a catastrophic thermal spike. Suddenly, the drone's surface temperature rockets upward, making it highly visible to long-range thermal sensors.
And the sources note that as the skin temperature spikes to extreme levels, say, approaching 700 degrees Celsius due to the trapped internal heat combined with the aerodynamic friction of flight, a physical phenomenon dictated by Wien's displacement law occurs.
Yes, Wien's displacement law is a huge factor here.
Can you explain that law? Because it seems critical to why the traditional stealth fails.
Wien's displacement law basically states that as the temperature of a blackbody radiator increases, the peak wavelength of its emitted radiation becomes shorter. At standard operating temperatures, an aircraft emits the vast majority of its thermal energy in the mid-wave infrared or long-wave infrared bands.
Okay, MWIR and LWIR?
Right. But as that heat accumulation trap causes the skin temperature to surge to 700 degrees, the peak radiation frequency physically shifts left on the electromagnetic spectrum.
It shifts into a shorter wavelength.
Exactly. The peak emission shifts directly into the shortwave infrared band, or SWIRE. And this shift is devastating to traditional stealth because standard low emissivity coatings and thermal camouflage patterns are not engineered to absorb or mask SWIRE wavelengths.
Ah. So the moment the drone overheats, it not only illuminates with greater intensity, but it radiates in a frequency band that completely bypasses its own camouflage.
The thermal containment strategy actively defeats itself.
Wow. So the engineers face a severe paradox here. They must hide the thermal radiation from the missile seeker head, but they absolutely must allow the internal waste heat to escape. Otherwise, the platform melts down and shifts into the highly visible SWIRE band anyway.
It's a massive contradiction.
So we need a surface material that acts like a highly selective one-way thermal valve, right? It needs to look completely cold to an enemy sensor looking up at it, but still somehow sweat out massive amounts of internal engine heat.
And this specific paradox led to the development of the technology that really dominates the thermal section of these documents. They are called wavelength selective thermal regulators, or WSTR.
WSTR, how do those work?
Well, to understand how WSTR functions, we have to look closely at the operational parameters of infrared-guided munitions and thermal imaging systems. A thermal camera does not simply ingest the entire infrared spectrum. It is specifically calibrated to hunt within narrow, clearly defined atmospheric windows.
Atmospheric windows. Because the Earth's atmosphere is a chaotic mixture of gases, right? You've got water vapor, carbon dioxide, methane, ozone.
Right. And these specific molecules act as opaque walls to certain wavelengths of infrared light. If a missile tries to track a target using a wavelength that water vapor absorbs, the thermal signal will dissipate into the ambient humidity within a few hundred yards. The missile would be blind.
So aerospace defense systems are engineered to look strictly through the clear windows in the atmospheric spectrum, where the infrared light can travel for tens or hundreds of miles without being absorbed.
Precisely. And the two primary atmospheric windows utilized by defense systems are the mid-wave infrared band, spanning 3 to 5 micrometers, and the long-wave infrared band, spanning 8 to 14 micrometers.
So if an aircraft emits thermal energy at 4 micrometers or 10 micrometers, a seeker head will detect it with perfect clarity.
Exactly. Now, the WSTR coatings, which frequently utilize intricate metamaterials or microscopic core shell structures like germanium surrounding a silicon dioxide core, they are engineered at the molecular level to manipulate their emissivity based on the exact wavelength.
Okay, the mathematical precision of these metamaterials is just staggering. The documents show that within that critical 3 to 5 micrometer window, the WSTR coating's emissivity is aggressively suppressed down to 0.21.
Right, almost nothing.
And in the 8 to 14 micrometer window, it is driven down to 0.17. So when a Stinger missile's sensor array, staring through those specific clear windows, looks up at the drone, the airframe appears to be radiating almost zero energy.
To the missile, the drone perfectly matches the thermal background of the cold night sky. It is thermally inert.
But wait, we still have the heat accumulation problem. The internal waste heat must be evacuated.
And this is where the selective nature of the WSTR coating is just brilliant. Remember the gases in the atmosphere, the water vapor and carbon dioxide that create the opaque, foggy bands where missiles cannot see?
The blind spots in the spectrum. The band spanning 5 to 8 micrometers and 14 to 20 micrometers where the atmosphere strongly absorbs thermal radiation.
Exactly. The WSTR metamaterial is structurally tuned to possess a massive emissivity, scaling from zero point 0.5 up to 0.82 exclusively within those atmospheric blind spots.
Oh, wow.
Yeah. The drone acts as a highly efficient black-body radiator, specifically at 6 micrometers and 16 micrometers.
That is an incredibly elegant exploit of environmental physics. The WSTR coating is taking the extreme internal waste heat, converting it into specific wavelengths of infrared light that the enemy seeker heads are completely blind to, and blasting it out into the atmosphere.
Yes. And because those specific wavelengths are highly absorbed by water vapor and carbon dioxide, the heat signature is immediately swallowed and dissipated by the air itself within a matter of feet.
And what does the empirical testing say about this? Does it solve the overheating?
Completely. In wind tunnel environments, simulating aerodynamic heating at Mach 2.2, utilizing this selective radiation cooling mechanism dropped the absolute surface temperature of the test article by an astonishing 72.4 degrees Celsius compared to traditional low-emissivity metallic coatings.
A 72-degree drop just from tuning the wavelength.
It entirely resolves the heat accumulation trap by utilizing the chemical composition of the atmosphere as an active thermal sink.
Okay, so that addresses the ambient heat radiating off the structural skin of the drone. But the physical exhaust plume presents a completely different challenge. You cannot paint a jet of 550-degree exhaust gas with a metamaterial.
No, you definitely can't.
You have a highly energetic, turbulent stream of fire exiting the rear of the propulsion system.
Right. And for the exhaust plume, the engineering shifts from material science back to aggressive fluid dynamics. The objective here is to rapidly cool the exhaust gas before it completely exits the airframe boundary.
And the specifications mandate the integration of two specific things: S-ducts and lobed ejector nozzles.
Yes. The S-duct geometry serves a very specific optical purpose first. If you run a straight exhaust pipe from the turbine out to the tail, you create a direct line of sight. A thermal camera positioned directly behind the drone can literally look straight at the tailpipe and see the glowing hot turbine blades.
Which is a dead giveaway.
Exactly. By curving the exhaust channel into an S shape, the physical geometry breaks the optical line of sight. The seeker head just sees the cooler, curved wall of the duct.
But the physical temperature reduction of the gas itself relies heavily on the lobed ejector nozzle.
It does. A standard circular exhaust nozzle simply expels the hot gas in a concentrated cylindrical column, which takes a significant amount of time and distance to mix with the ambient air and cool down. A lobed ejector nozzle drastically alters this flow.
How is it shaped?
Instead of a perfect circle, the nozzle is shaped like a complex corrugated star or like a wavy flower petal. As the high-velocity, 550-degree exhaust gas blasts through this complex geometry, it drastically increases the perimeter area of the flow.
Right, because instead of a smooth circle, you have all these folds and ridges. Increasing the perimeter area maximizes the shear layer between the high-speed burning hot exhaust gas and the slow-moving, freezing cold ambient night air.
Exactly. The severe shear layer induces massive Kelvin-Helmholtz instabilities.
Kelvin-Helmholtz instabilities.
Yeah, they are highly turbulent fluid vortices that fold the hot and cold air into one another. The geometry of the lobe nozzle acts as an immense fluidic vacuum. It physically entrains vast quantities of cold bypass air from channels built into the drone's fuselage, and violently mixes it directly into the core of the exhaust plume.
So it forces a chaotic, turbulent mixing process inside the nozzle geometry before the gas ever hits the open air.
Yes. And the S-duct and lobed ejector combination is so efficient in entraining cold bypass air that it dilutes the 550-degree exhaust gas down to under 70 degrees Celsius prior to atmospheric ejection.
That is a massive temperature drop in a fraction of a second.
Right.
But to handle the immense thermal stresses inside the S-duct during that mixing phase, the components are manufactured from carbon silicon carbide, or CS ceramic matrix composites.
Yeah, CSM maintains incredible structural integrity at extreme temperatures and has very low thermal conductivity, ensuring the tailpipe itself doesn't glow and become a secondary heat source.
But the thermal stealth engineering in these documents contains one final, highly advanced countermeasure aimed at a specific vulnerability: the moving background problem.
This is where it gets really sci-fi.
It really does. So the WSTR coatings and the exhaust mixing systems are designed to make the drone run as cold as possible, but thermal camouflage is relative, right?
Completely relative.
If a drone is tuned to emit a thermal signature equivalent to 10 degrees Celsius to perfectly match the cold night sky, it is effectively invisible. However, if that drone alters its flight path and banks low in front of a terrestrial background, such as a sun-baked rock face or a warm desert floor radiating at 30 degrees Celsius, the drone's static camouflage fails instantly.
Because it becomes a negative silhouette. A 10-degree object moving across a 30-degree background looks like a giant, unnatural black hole on a thermal imaging screen.
A cold spot is just as anomalous and trackable as a hot spot.
Exactly. The drone has to be able to dynamically alter its apparent temperature to match a rapidly shifting background. And the sources detail an experimental approach to this, utilizing multi-layer graphene and ionic liquids.
Graphene.
Graphene is a remarkable nanomaterial. It consists of a single layer of carbon atoms arranged in a hexagonal lattice. It possesses highly turnable optical and electronic properties. The engineering teams layer this multi-layer graphene structure with a room temperature ionic liquid.
And what does the liquid do?
It functions as a highly conductive electrolyte gating medium. This composite structure is applied directly to the exterior skin of the platform.
Essentially turning the skin of the drone into an electrochromic capacitor.
Yes. The drone's onboard sensor suite continuously monitors the ambient thermal radiation of the background environment. When the computer detects that the drone is transitioning from the cold sky to a warm terrestrial background, it applies a minute electrical bias, a tiny voltage across this graphene ionic liquid skin.
And what happens when that voltage hits?
When that voltage is applied, the electrostatic field drives ions from the liquid directly into the microscopic gaps between the individual graphene layers. This process is known as ionic intercalation.
Ionic intercalation.
Right. Crucially, the introduction of these ions fundamentally alters the chemical potential, or the Fermi level, of the graphene structure.
The Fermi level. Okay, so by shifting the Fermi level, you are physically manipulating the density of states of the electrons within the carbon lattice.
You are. This electrostatic doping alters how the graphene interacts with photons. In a fraction of a second, shifting the Fermi level modulates the optical conductivity of the skin, which precisely dictates how much infrared radiation the graphene absorbs and emits.
Oh man, so the flight computer can literally dial in the exact emissivity required to force the drone's apparent temperature to perfectly match the 30-degree mountain behind it.
Yes. And when the drone clears the mountain and flies back over a cold river, the voltage is reversed. The ions retract, the Fermi level resets, and the drone returns to a 10-degree apparent signature.
It is a fully dynamic electrochemical thermal camouflage system that completely neutralizes the cold spot vulnerability.
It's like a thermal chameleon.
Exactly. So you've got a system that is perfectly dark to sound and dynamically imperceptible to heat. But by completely sealing the drone structurally to trap the acoustics and wrapping it in advanced metamaterials and graphene to control the thermals, you inadvertently create an inescapable cage for internal electromagnetic energy.
You do. You create a huge EMI problem.
Because a modern heavy payload drone is essentially a violent thunderstorm of high-voltage electricity. We are talking about dense battery packs pushing hundreds of volts and massive continuous currents to the propulsion systems. Pumping that much electrical power around a confined space generates a massive volatile electromagnetic field.
A huge field.
And if you don't contain it, that field screams into the radio frequency spectrum, completely illuminating the drone to enemy electronic warfare radars.
The internal electromagnetic interference, or EMI, generated by these high-power propulsion systems is staggering.
Yeah.
It represents the most complex shielding challenge on the entire platform. The source documents specifically isolate the electronic speed controllers, the ESCs, as the primary source of this severe broadband noise.
Why the ESC specifically?
Because modern ESCs designed for high-efficiency drone platforms do not utilize standard silicon transistors anymore. They rely on wide bandgap, or WBG, semiconductor switching architecture, utilizing silicon carbide, or CC, and gallium nitride, or GaN.
Okay, the use of silicon carbide and gallium nitride is mandated because they allow the drone to operate at much higher voltages and higher temperatures without suffering thermal breakdown, right?
Right. But here's the issue. The ESC doesn't just send a smooth, flat, continuous flow of direct current from the battery to the motor. To drive the brushless motor efficiently, the ESC chops the direct current into incredibly fast, high-voltage pulses. It rapidly switches the power on and off thousands of times a second to create an artificial alternating current.
And the issue stems from the physical properties of those wide bandgap materials, doesn't it?
It does. Because GaN and SiC have such high electron mobility, they transition from an off state to an on state violently fast. The slew rate is phenomenal. The voltage spikes from 0 to several hundred volts in a matter of nanoseconds.
And in electromagnetic theory, a sharp, near instantaneous change in voltage over time, a massive dVdt, is the exact mechanism that generates high-frequency radio waves.
Exactly. If you run a Fourier transform on a perfect instantaneous square wave, you will see that it contains an infinite spectrum of high-frequency odd harmonics. By utilizing these hyper-efficient WBG semiconductors, the ESC is blasting out extreme transient voltage spikes, turning the entire internal circuitry into a broadband radio transmitter.
The ESC is essentially a localized radio jammer operating inside the drone's fuselage.
It really is.
Yeah.
And the severe EMI environment poses a twofold threat. First, it easily propagates through the airframe and triggers enemy electronic support measures, alerting them to the presence of a high-power electrical system. But more critically, it induces self-jamming. The high-frequency noise couples into the drone's own internal avionics.
Right, because the drone has to navigate, meaning it relies heavily on GNSS, or GPS signals. And a GPS signal originating from a satellite orbiting 12,000 miles away is unbelievably weak by the time it reaches the antenna on the drone's back.
We are talking about signal strengths in the realm of negs of 135 dBAna.
It is. So to prevent self-jamming and external detection, this electrical storm must be absolutely contained. Now, in standard automotive or consumer electronics, if you have a noisy component generating common mode currents, the standard engineering practice is to simply ground the component to the massive metal chassis of the vehicle, right?
Sure, the metal frame acts as a massive sink, soaking up the interference.
But applying that logic to a drone platform built primarily from carbon fiber reinforced polymers is a recipe for a catastrophic mid-air failure. We have to look closely at the highly specific anisotropic material properties of CFRP.
Yes, carbon fiber is not a homogeneous metal like a car chassis. It is a composite material made of highly conductive carbon filaments woven together and suspended in a highly resistive epoxy resin matrix. This creates extreme electrical anisotropy.
Anisotropy meaning the material exhibits vastly different physical properties depending on the direction you measure it.
Exactly. If you attempt to pass an electrical current longitudinally along the continuous path of the woven carbon fibers, the conductivity is reasonably high. However, if you attempt to pass that same current transversely across the plies, the current hits the insulating epoxy resin. The cross-sectional resistance is orders of magnitude higher.
So if an engineer attempts to utilize the CFRP airframe as a common ground plane for the high voltage ESCs, the severe high-frequency noise currents do not flow smoothly at all.
No, they don't. As the high amperage current encounters the high transverse resistance of the epoxy matrix, it generates intense localized heating. Pumping continuous high-frequency transient currents into carbon fiber causes the internal resin to literally melt, outgas, and delaminate the structural plies.
It literally destroys the structural integrity of the drone.
And in extreme fault scenarios, the localized heating will ignite the carbon fiber mid-flight.
Wow, grounding to the airframe induces structural fires. Furthermore, because the electrical resistance across the carbon fiber skin is so unpredictable and uneven, it creates massive voltage differentials across the chassis.
Right. And those voltage differentials drive intense common mode noise, physically turning the entire exterior skin of the aircraft into a massive, unpredictable dipole antenna that radiates the exact WBG switching noise you are attempting to suppress.
So grounding to the composite structure is strictly forbidden in the specifications. Instead, to manage the immense internal noise currents, the engineering protocols mandate the implementation of a star ground bus topology.
Star ground bus. It is a highly disciplined, rigid approach to electrical architecture. Instead of allowing various subsystems to ground to the nearest structural hardpoint, the engineers install a single, highly conductive, physically isolated hub, typically machined from pure copper or aluminum at one highly specific centralized location within the fuselage.
And every single electrical circuit on the platform, from the massive high-power ESC phase lines all the way down to the sensitive low-voltage 5-volt microcontrollers handling the GPS arrays, must route an individual dedicated ground return wire all the way back to this exact physical hub.
It resembles the spokes of a wheel, converging on a single central hub. By forcing every reference potential on the aircraft to physically meet at exactly one singular point in space, you mathematically eliminate the possibility of ground loops.
Can you clarify ground loops for the listener?
Sure. A ground loop occurs when two different components are grounded at different locations on a chassis that has intrinsic electrical resistance. Because of that resistance, ground point A might be sitting at 0.1 volts, while ground point B is sitting at 0.2 volts.
Right.
That tiny voltage differential causes parasitic currents to flow across the chassis between the 2 points, generating magnetic fields and radiating noise.
So the start ground bus ensures that no such voltage differentials can exist because there is only one physical ground reference. The severe high-voltage noise currents generated by the ESCs are forced directly back to the battery source through dedicated lines, completely bypassing the delicate low-voltage navigation circuits.
Exactly. The violent electrical storms are kept strictly corralled in their own isolated loops.
Okay, the circuit loop issue is solved by the start topology. But we still have the physical transmission lines to deal with. The heavy gauge cables carrying hundreds of volts from the battery to the ESC and the phase lines running from the ESC to the motors act as massive radiating antennas. The high DVDT transient spikes travel down these wires and blast RF noise into the internal cavity of the drone.
Right, and this is where the engineering adheres strictly to MIL STD 461G.
Which is the military standard for electromagnetic interference characteristics.
Yes. To prevent the cables from radiating, every single high-voltage transmission line must be encased in a dense, tightly woven, metal-braided shield. It effectively surrounds the noisy conductor with a flexible metal pipe.
Now, the concept of a shielded cable is standard practice, but the military specification for how that shield is terminated at the connector is where the true EMI suppression occurs. The source documents contain explicit, severe warnings against a common wiring practice known as pigtail termination.
Oh, pigtails are a massive vulnerability at these frequencies. In standard consumer electronics manufacturing, when a technician needs to ground a shielded cable, they will frequently strip back the outer insulation, gather the woven metal braid, twist it tightly together into a single thick wire, which resembles a pig's tail, and solder that single wire to a grounding pin on the connector.
At low frequencies, a pigtail is a perfectly acceptable electrical ground. But at the extreme high frequencies generated by gallium nitride ESCs, that physical twist becomes a severe problem.
It becomes an induction point. At high frequencies, electrical current travels primarily on the surface of the conductor, a phenomenon known as the skin effect. When the broad, uniform surface of the braided shield is suddenly choked down and twisted into a single narrow pigtail wire, the inductance of the connection skyrockets.
That tiny twisted piece of wire suddenly presents a massive impedance barrier to the high-frequency noise trapped inside the shield.
Exactly. Because the noise current encounters this massive impedance bottleneck at the pigtail, it cannot flow smoothly into the ground. Instead, the electrical energy backs up, and the pigtail itself begins to act as a highly efficient, concentrated, omnidirectional antenna.
It takes all the severe EMI trapped inside the cable shield and violently radiates it straight out into the drone's internal electronics bay. The pigtail entirely defeats the purpose of utilizing a shielded cable in the first place.
To eliminate the pigtail inductance problem, MIL STD 461G explicitly mandates a 360-degree circumferential bond at every single connector interface.
So how do you do a 360-degree bond?
It requires specialized backshell hardware. Instead of stripping and twisting the shield, the technician carefully spreads the metal braid out evenly and clamps it tightly around the entire outer circumference of the metallic connector housing. It creates a seamless, continuous, 360-degree metal-to-metal contact ring all the way around the cable junction.
And this specific geometry is critical because the 360-degree bond ensures that the transfer impedance, the resistance to those high-frequency surface currents, is kept incredibly low, typically in the low milliohm range.
Exactly. When the high-frequency electromagnetic wave travels down the shield, it encounters a smooth, massive surface area at the connector. The noise current flows perfectly and harmlessly into the grounded connector housing without ever encountering an inductive bottleneck or a physical gap to leak out of. It seals the transmission pipe entirely.
The level of rigorous, paranoid attention to detail required to trap those transient spikes is incredible. But the shielding logic extends beyond just the wiring harnesses. The physical components themselves, the ESC housings, and the massive electric motors must be converted into inescapable microfaraday cages.
Yes. The ESCs are typically housed in heavy machined aluminum enclosures. Aluminum provides excellent attenuation for high-frequency electromagnetic waves. However, an enclosure is not a solid block. It is composed of multiple parts bolted together.
Right, there's a lid and a base.
And any seam, any joint where two pieces of metal meet, regardless of how tightly they are machined, contains microscopic air gaps due to surface roughness.
And high-frequency microwaves are incredibly small. A 10 gigahertz RF wave has a wavelength of roughly 3 centimeters. It will easily squeeze through a microscopic gap between two bolted plates and radiate out into the fuselage.
So to seal these microscopic leak paths, the engineers employ military-grade conductive elastomers.
A conductive elastomer is essentially a rubber gasket engineered to conduct electricity, right?
Right. The manufacturing process involves taking a highly durable, weather-resistant silicone polymer matrix and heavily impregnating it with microparticles of highly conductive metals, specifically silver-plated aluminum.
Silver-plated aluminum inside silicone.
Yeah. And the loading density of these metal particles is pushed past what's called the percolation threshold. This ensures that the particles physically touch one another continuously throughout the rubber matrix, creating thousands of microscopic electrical pathways.
So when the aluminum lid is screwed down onto the ESC housing, this silver-laced silicone O-ring is aggressively crushed into the seam.
Exactly. The mechanical compression serves two purposes simultaneously. The silicone matrix provides a watertight, IP67-rated physical seal, protecting the sensitive WBG semiconductors from atmospheric moisture and humidity.
But more importantly, the crushed silver particles create a continuous low-impedance metal-to-metal electrical contact entirely across the seam.
The conductive elastomer effectively welds the two halves of the aluminum enclosure together electrically. The source documentation indicates that applying these specific conductive seals provides up to 120 decibels of continuous high-frequency shielding effectiveness.
The Faraday cage is completely sealed, utterly trapping the violent broad-spectrum emissions of the gallium nitride switches inside the box.
That secures the ESC. But the final component in the propulsion chain is the electric motor itself. And an electric motor is fundamentally open to the environment. It is a spinning outer bell and open vents to allow airflow to cool the internal stators. You cannot put a solid aluminum box over a spinning motor.
So how do you electromagnetically shield the exposed high-voltage copper coils that are physically generating the massive rotating magnetic fields required for flight?
Shielding an open-air motor requires the most extreme material intervention in the entire EMI strategy. The core of the motor is the stationary central hub, containing the dozens of tightly wound copper coils. These coils are passing massive high-frequency alternating currents, radiating severe EMI directly into the air.
So how do they stop it?
The engineers solve this by utilizing a technique called conductive stator potting.
Now, potting usually involves casting delicate electronics in a solid block of plastic resin to protect them from physical vibration. But standard epoxy resin is an electrical insulator. It is completely transparent to radio waves. The EMI would blast right through it.
Right, which is why the specifications mandate the use of a highly specialized conductive epoxy resin. The chemical formulation of the epoxy is heavily laced with complex carbon-based conductive fillers, such as carbon nanotubes or dense suspensions of metal microparticles.
And the manufacturing process involves placing the entire wound copper stator assembly into a vacuum chamber and injecting this highly viscous metal-laced epoxy directly into the core, completely saturating the coils.
The entire copper coil architecture is entombed in a solid block of electrically conductive plastic.
And this rigorous process achieves 3 critical objectives, doesn't it? First, the solid epoxy mass provides immense mechanical rigidity, preventing the copper wires from vibrating and fatiguing under the extreme acoustic and aerodynamic stresses of flight.
Yes. Second, the epoxy itself provides tremendous dielectric insulation, preventing the high-voltage coils from suffering catastrophic short circuits against one another. But the third and most crucial objective for the self-triad is the electromagnetic containment.
Because the epoxy is heavily laced with conductive carbon or metal particles, the solid block physically acts as a continuous microfaraday cage molded directly around every individual strand of copper wire.
Exactly. Any high-frequency electromagnetic radiation generated by the DVDT transients in the coils immediately encounters this conductive matrix. The conductive particles within the epoxy absorb the electromagnetic wave energy, converting a portion of it to minute thermal heat through resistive losses and rapidly shunting the remaining interference currents directly to the star-ground bus path.
The severe internal electrical storm is aggressively swallowed at the exact point of generation before the waves ever have a chance to leave the physical casing of the motor.
It's just phenomenal engineering.
It really is. Let's pull all of these disparate threads together because the sheer scale and complexity of the engineering we've analyzed today is just staggering. We began by asking how a massive machine flying through the night sky could simply cease to exist on every detection spectrum. And what these technical documents reveal is that absolute stealth is not achieved through a single magical coding or a single piece of hardware.
No, it's achieved through an absolute, uncompromising, microscopic war of attrition against the fundamental laws of physics.
It is a war fought simultaneously across fluid dynamics, thermodynamics, and electromagnetics. On the acoustic front, they are calculating the precise Reynolds numbers and pressure gradients to slice 0.12-inch double-depth grooves exactly at the 0.95 radial mark, violently shearing the tip vortices before they can form.
Right, they're biomimetically replicating the aeracoustics of owl feathers to scatter mechanical hum into high-frequency white noise that the atmosphere naturally eats.
They are filling carbon fiber resonant chambers with highly cross-linked polymethacrylamide foam to convert vibration into friction, and they are utilizing 12-bit rotational encoders to physically force the engines to actively destroy each other's pressure waves in midair.
And on the thermal front, they're manipulating the Fermi levels of multilayer graphene with ionic liquids to dynamically shift their emissivity on the fly.
They are layering germanium and silicon dioxide metamaterials to act as a one-way thermodynamic mirror, aggressively restricting radiation in the 3 to 5 and 8 to 14 micrometer bands, while exploiting the atmospheric absorption bands at 6 and 16 micrometers to secretly dump immense waste heat directly into the water vapor of the sky.
They are utilizing carbon silicon carbide S-ducts and lobed ejectors to induce Kelvin-Helmholtz instabilities, violently entraining ambient air to passively erase the exhaust plume signature.
And finally, on the electromagnetic front, they are confronting the immense chaotic DVDT transients generated by wide-band gap gallium nitride semiconductors. They are mapping the anisotropic resistance of carbon fiber to design pure copper star ground bus topologies, entirely eliminating common mode ground loops.
They are strictly enforcing MIL STD 461G by utilizing 360-degree circumferential backshells to drop transfer impedance and eliminate pigtail antennas.
They are crushing silver-plated aluminum elastomers into microscopic seams to achieve 120 decibels of continuous shielding, and they are vacuum potting the very heart of the propulsion system inside solid blocks of carbon-laced epoxy, forming absolute microfaraday cages around the high-voltage coils.
I mean, the broader implication of this deep dive, the reason this engineering is so profound is that it completely redefines the concept of technological innovation. We traditionally view engineering as a process of forcing a machine to impose its will on the environment. We build stronger, faster, hotter engines to overcome drag and gravity.
We focus entirely on amplifying the presence and the power of the machine.
But true, bleeding-edge signature suppression requires the exact opposite philosophy. It demands an intimate molecular-level understanding of the surrounding environment. It requires knowing the exact atomic absorption spectra of carbon dioxide in the upper atmosphere.
It requires mapping the Kolmogorov microscale cascades of turbulent boundary layers.
It requires understanding the parasitic capacitance of anisotropic composites at 10 gigahertz. The engineers are not trying to overpower the environment. They are meticulously analyzing the structural blind spots of the physical universe, and they are engineering platforms that perfectly conform to the shape of those blind spots. It's the absolute mastery of negative space.
Mastering the negative space. That is a great way to put it. And it leaves a haunting philosophical question for anyone tracking the future of aerospace detection. We have spent this entire deep dive analyzing how engineers are systematically, methodically erasing every single energy emission a platform generates. They have collapsed the acoustic waves, swallowed the thermal radiation, and caged the electromagnetic storm. The machine literally blends into the background static of physics itself. If the platform emits absolutely nothing, wait, how do the next generation of defense systems ever find it?
That is the million-dollar question.
The entire paradigm of radar and thermal tracking is based on detecting a positive signal against a noisy background. But if the signal is zero, the paradigm fails. Will we be forced to abandon the search for positive emissions and instead train artificial intelligence models to hunt for the distinct absence of natural
Like
signals?
looking for a hole in the data.
Right. Will the radars of tomorrow be forced to look for an inexplicable, localized hole in the cosmic background radiation? Will they have to scan for an unnatural patch of absolute silence within the ambient wind, or a tiny, moving shadow occulting the thermal noise of the stars?
The engineering trajectory suggests exactly that. We are moving from the detection of energy to the detection of the void.
The detection of the void. Think about the complexity of that the next time you stare up into the darkness of the night sky, trying to discern if there is a massive, incredibly complex machine, perfectly silent, dynamically cold, and electromagnetically dark, flying directly overhead.